have this image of the world back when we believed that everything revolved around the earth. So you have the spheres.
Mm-hmm.
So you have the earth, you have the heavens, the sky, then you have the heavens, the stars, and this almost this picture of a bubble, a very large bubble, but a bubble around the earth that contains all the stars, the planets, the sun. And then outside of this shell, you have God.
Yeah.
The more that we understand about the universe, now we know that the observable universe, the only part, the part that we can see, is about 64 million light years across. And so, and it could go on infinitely beyond that. We don't know. But our image of God, because we know that God is being itself, and God created everything, that God is so much bigger than that.
3, 2, 1. Welcome to Mathematician.
Welcome to another Nerding Out. I'm here with my, as always, awesome co-nerd, Cesar. We are talking today about the history of math, and this, unfortunately, is our last episode in the history of math. It's not the last episode in math, but we have been working through this series on the history of math, starting all the way back in the ancient world, and today we're coming up to modern times. Before we get into that, I just want to remind you that if you want to keep in touch with what we're doing, if you want to know what's the latest thing with the Nerdy Catholics, the best way is to go over to thatnerdycatholic.com and sign up for our email list. We promise that we won't spam you. Probably send an email or two a month letting you know about new videos are up, new opportunities to support us, and other things like that. If you think we have earned it, we would love it if you would subscribe to this video. If you're watching on YouTube, like this video and share it with your friends. If you're listening to this as a podcast, we'd love for you to be able to rate our episodes, our show on the podcast platform that you use. And lastly, if you like the merch that we have, t-shirts, we got some Nerding Out and Nerdy Catholic mugs. You can head over to thatnerdycatholic.com/merch and get merch of your own. So we are ending our series on the history of math, Cesar.
Yep.
Who are we starting out with?
So let's start with one mathematician that talks about infinity.
Okay.
Let's talk about Georg Cantor. So Georg Cantor, he was born in St. Petersburg back in the 1845. And he was really a devout Christian as also a mathematician. No? So one of the contributions that I've seen a lot that has impacted Georg Cantor's work was the set theory and also the cardinal and ordinal numbers. So I didn't know that until at that time, 1, 2, 3, 4, 5, if it was different from first, second, third, fourth, no. And we will see why this separation of cardinal and ordinal. No, in the beginning, I will say that although the concept might be centuries ago, he's the one that declared cardinal as cardinal number and ordinal as an ordinal number.
So why did he do that? What was the purpose for him coming up with these definitions?
So that's an instrument from him to grasp infinity.
Oh, okay.
Which is, I mean, that's the biggest topic, no, here. So he's the one that proposed that there are different levels of infinity. No? I say, for me, when I hear this, it was kind of weird. It's, what about infinity? I mean, there's an infinity and that's it, no? And it happens that no.
No. Yeah, infinity just goes on forever, right?
Yes.
If you think of infinity, well, infinity just means it never ends, right?
Yes.
But actually, that's infinite, not infinity.
Yeah. Exactly. That's a good point.
Yeah.
Yes. One of the things that Georg Cantor started to notice is that, for example, the numbers 1, 2, 3, 4, 5, 6 can go to infinity. No. But then, you know, if you ask, for example, what about the even numbers, no?
Mhm.
2, 4, 6. That goes to infinity too, no?
Yeah.
And he discovered that, and that's how we got set theory and cardinal and ordinal number, no?
Mhm. So what is set theory then? Thinking about infinity.
So, first of all, what is set theory
Mhm.
per se? No, set theory is the theory about how do you the study of sets,
Mhm.
whatever that contains inside. No,
Mhm.
it's a set of numbers. So, for example, if we are talking about the even numbers, no,
Mhm.
there's a set of 2, 4, and if you want to describe that set, you can mathematically describe that
Okay.
set.
So you could say if you have the set of even numbers, if you have a number, if it's even, it's in that set. If it's odd, it's outside of that set.
Exactly.
So it's a way of grouping numbers. Okay.
Exactly. That's a nice thing. No? And you can say, for example, the set of even numbers are all natural numbers
Mhm.
that are 2 or a multiple of 2.
Right. So you can come up with, say, here's a set, and here's the mathematical definition of what it means to be in that set
Yes.
or outside of that set.
And there's also you can apply some properties that apply to the numbers in that set,
Mhm.
and that property that
Okay.
applies to. So that concept of set comes from Cantor.
Okay.
No? The other thing that it's important to mention is that, as I mentioned before, the ordinal and cardinal numbers. No,
Mhm.
so when he started studying infinities, he said, "Okay, which is the first number of this infinite set?
Mhm.
No? Which is the second number?" So, for example, in the set of even numbers, you can type the first number is 2, the second number is 4, the third number is 6, and you can go on infinity. But there's, for every number in that infinity set of even numbers,
Mhm.
there's a
There's a
cardinal number.
Yeah.
No.
Okay. Okay. So the numbers then in the cardinal numbers, first, second, third, fourth,
Yeah.
have nothing to do with the value of the number.
Yes.
It
Yes.
defines their place within a set.
Exactly.
Okay.
Exactly.
Okay.
But then that's when things get a little trickier, no? Because you will say, well, infinite is infinite, no?
Mhm.
Then he made a statement that says, there are more numbers, there are more real numbers between
Mhm.
0 to 1 that in the natural numbers. No?
Mhm.
So, and what does he say?
Yeah.
Why
Yeah.
does he say this? No?
Yeah.
And you start trying to take a correlation. Okay, both are infinite sets of numbers.
Yeah. Yeah.
But then you have to account that for example, if we take the natural number 1 is the first number, number 2 is the second number, and you can go to infinity. But you can attach one position. In the real numbers between 0 and 1, okay, 0.00001, let's say, is the first one.
Yeah.
But you can always have a number between two numbers.
Yeah. Well, you can always add a zero.
Yes.
Another zero between the
the
decimal
initial
and
point and the first number.
Yeah.
And then,
So 0.001.
Uh-huh.
Okay. Well, you can have a bunch of numbers with that many digits after the decimal. You add one more zero, 0.0001. You can keep adding zeros. Yeah.
Yes.
Yeah. I remember the time when I learned that, and I realized that there are an infinite number of numbers between 0 and 1. And so then you have that number. Yeah, it blows your mind. But to think that if you have the number of real numbers between 0 and 1 is infinite.
Yeah.
And the number of real numbers between 1 and 2 is infinite. So if you have the whole numbers are infinite, well, then just between 0 and 2, you have double that.
Yes, exactly. And you may say, how does this happen? No?
Yeah.
And that is that we have to grasp the concept that there's an infinite set of numbers that are countable, but there's an infinite set of numbers that are not countable.
Yeah, and we haven't even started talking about negative numbers.
Oh yeah, oh yeah, and we didn't have started imaginary numbers either. Yeah. So, or numbers in two or three, expressed in 2 or 3 dimensions, like
Mhm.
vectors or
Yeah.
matrices.
Or having a variable to a variable.
Yeah,
Or,
there you go.
I mean,
So
there's once you start thinking about different levels of infinity, you can start imagining a number of different levels. I mean, we can't imagine an infinite level because we can't imagine
Ex-
infinity, but
yeah, and the idea that there's an infinity that is greater than another infinity because it's
Mhm.
contained into that.
yeah.
That's such a powerful
Yeah.
idea,
Yeah.
really.
So what was his view on God?
He was a Christian,
Mhm.
But what struck me is that when he came up with this theory of infinite, many, even Christian mathematicians criticized him that he was saying that he was, let's say, going against God
Mm.
because he was defying the infinite power of God.
Mm.
No?
Mhm.
And I really lament this, that there's a misunderstood so
Mhm.
deeply
Yeah.
on his theory. That has nothing to do with God. And even Cantor said
Yeah.
this is not about God. This is about, he even said that concept of the infinity of infinity was revealed to him, to God.
Mhm.
Not, he was not challenging God. He was
Mhm.
acknowledging that God is his inspiration
Mhm.
of this theory.
Yeah. It's a humbling thought, and it's something that we still need to be very wary of today. That
Yeah.
as we've said many times before, if it's true, then it's true. That there's no talking about set theory. We don't have sets of truth.
Yeah.
We don't have a set of scientific truth here, mathematical truth here, theological truth here, philosophical truth here, that aren't connected to each other.
Mhm.
If it's true, God is the author of all truth.
Yes.
And so if something is true, then it means it is something that God has authored. It is so easy to have a view of God that is so much smaller than God actually is.
Yes.
So to say, if you're studying an infinite set of infinities, then you're going against the infinite power of God. Well, God is, the way Aquinas puts it, God is what is, or that's how it's defined in the Bible.
I am who I am.
I am who I am,
Mhm.
and to say I am, it doesn't say I'm here. It says I am.
Mhm.
That Aquinas said God is being itself. God is not a being.
Mhm.
And you look at a lot of the books written by a lot of modern atheists
Mhm.
have a very small view of God.
Oh yeah.
Right.
Yeah.
And to say, and they would probably go along with these people that were saying these things about Cantor, that they would say that the infinite set of infinities disproves God,
Exactly.
but that's also disproving a very small God.
And I know that this is a topic for another episode, but that reminds me. Just a couple of years ago, they were talking about the Higgs boson, that was the particle of God.
Oh yeah, the God particle.
Yeah, so that's how reduced, that's how little they consider God. God is this part.
Yeah.
Come on. Okay.
Yeah.
But I love the humility, as you mentioned. I love the humility of Cantor. He admits this is an inspiration of God to me, and this is not by defying any of his majesty or his power or nothing like that.
Yeah.
This is something that is true because he explained that.
Yeah. I would even say that the more that we learn about the world through science, through math, the bigger our picture of God can become.
Yes.
I had this image of the world back when we believed that everything revolved around the earth. So you have the spheres. So you have the earth, you have the heavens, the sky, then you have the heavens, the stars, and this almost this picture of a bubble, a very large bubble, but a bubble around the earth, that contains all the stars, the planets, the sun, and then outside of this shell you have God.
Yeah.
And you could almost have an image of the image we have now of this big old white guy sitting on a throne, because the size of the universe in our minds back then was so small.
Yes.
The more that we understand about the universe, now we know that the observable universe, the only part, the part that we can see, is about 64 million light years across.
Mm-hmm.
And so, and it could go on infinitely beyond that. We don't know.
Mm-hmm.
But our image of God, because we know that God is being itself, and God created everything, that God is so much bigger than that.
Oh yeah.
So our image of God keeps getting bigger and bigger, not because the phrase that I hear a lot, the God of the gaps.
Yeah.
That one argument against God is that, well, you're just saying that God did something because it's something you don't understand anymore. The more we understand, the more we can say, well, that God didn't do that. We understand the mechanism behind this now.
Mm-hmm.
We understand the physics behind it or the chemistry behind it. So we can take God out of that picture.
Yep.
But really it's the opposite. The more you understand, the more awe you can have for the intelligence of the God that created everything.
For the intelligence of our Creator, definitely.
Yeah.
But the good news is that not everybody was against Cantor, no? And one of the guys that supports Cantor a lot was David Hilbert, no? And he's our next mathematician here, no? David Hilbert was a German mathematician. He was born in 1862, and he was also very influenced by Cantor, no? He entirely support Cantor, no? But Hilbert make many contributions. He is another greatest mathematicians of all time. No, he makes the idea of calculus variation, algebra, algebraic numeric theory, things that I don't attempt to explain here in this channel because it goes beyond right now my mind.
But we've talked about this, but I would love to at some point have an expert on, or a professor that actually understands this, because some of these things, as you said, no idea what they mean, but I would love to understand them more.
Yes, definitely. And that would be a good idea. I would love to have that too. So we'll stay tuned. Probably we'll soon have that. So right now, when we talk about Hilbert, we have to realize one of his biggest achievement, which is a Hilbert Complex Space. And why Hilbert Complex Space is such a big achievement? Because that's the math that we are using to define a quantum qubit.
Okay,
and
so
that's
the basis of the quantum computers. Yeah.
There you go, sir. There you go. There you go. It's amazing. Again, we are talking about a mathematician that died in 1943, and quantum computers start in maybe the 90s, probably.
Yeah. I mean,
or
in theory
this
in the
century.
90s, but I think it's just been within the last decade or so that we've actually been able to start building very basic ones.
So here I have another example of a mathematician that came with a thing that is used several years after. Probably when Hilbert said, "Oh, this is a nice theory. I love it." No, what application do I have? Got no idea.
Well, and it might have even been thinking it would be really amazing if someday we would be able to build a machine based on this in, I don't know, maybe 1, 2, 3,000 years.
And the funny thing, we are still building that machine. So it's, there is prototypes, but
I think right now, I haven't seen the latest, but I remember seeing a video a little while ago about a quantum computer that had, I think it was around 100 qubits in it.
Yeah.
I mean,
15 and 12 qubits.
Yeah.
Yes,
so,
exactly.
So the size, of these computers, the size is huge, but the computing power of them is very small at the moment.
Yeah.
But they're all, proof and concepts.
No, that's proof. That reminds me. You remember when we start with the normal computers and the ENIAC, which is I think
Oh,
twice the size
yeah.
of this room.
Oh, I remember going on a tour and of someone that had a huge mainframe
Uh-huh.
that was, multiple times the size of the studio. And I remember the guy saying, and now, look at the computer you have in your desk. Well, this was back in the 90s.
Yeah.
So this was still, the computers were pretty big compared to how we are now. Now you could, look at your watch.
Yes,
Look at
exactly.
your smartwatch and say your smartwatch has way more computing power than something that fit into an office.
And right now in quantum computing, we are in the ENIAC era.
Mhm.
So we haven't
Mhm.
even developed everything.
Yeah.
But there you go. The math, as always, the math
Yeah.
precedes. No,
By
the idea.
decades.
Exactly, exactly. So here Hilbert has this Hilbert Complex Space that allow how to describe the movement of a quantum bit. Let's call it qubit because that's how they call it, and what operations can be done.
Mhm.
And the funny thing is that they are not the same operation as a normal bit that we will have. There are different operations. No, the Hadamard transformer. There is a lot of operations that, and each operation is not 0 and 1, but a multiple possibilities of outcome that in the last moment, as the quantum as a quantum field, it just ended up in one possibility of the many that are on the computer.
When they say when it collapses.
Exactly.
Yeah.
Exactly.
Yeah. We had no idea of what quantum mechanics was at the time.
Mm-hmm.
We had no idea of it wasn't until the 20th century, throughout the 20th century, was the over the decades, the development of the understanding and the understanding of the structure in the atomic world. So he is working on this theory mathematically that then ends up describing what we discovered 100 years later about the structure of the quantum world.
Yes, yes, and that's a very nice application of bringing the quantum worlds into computer. No,
but even just the understanding of the quantum world.
Yeah.
Not even thinking about how to use it as a computer, but what does it mean? The uncertainty. Thinking about the Heisenberg uncertainty principle, which came later.
Yeah. And I wanna quote this because when you say understanding, people might think, oh, we understand the quantum world. When we say understanding, it's having the laws, the mathematical laws that describes how does this quantum world works. Because I want to quote Richard Feynman here. He said, and this was late in the 70s, he said, don't let them fool you. Nobody knows what exactly is quantum physics. And we are talking about Richard Feynman. I mean,
one of the smartest guys in the 20th century. Yeah.
Yes.
And if you don't know who Richard Feynman is, if you know the Fermilab in Illinois, it's the very large. I say it's large because in my mind it's not. The Very Large Hadron Collider is in Europe,
Switzerland, yeah.
But it's one of the large
biggest,
colliders in the United States.
Yes.
He helped found that. So he's a very smart mathematician and physicist.
Yes. He's one of the greatest minds in physics in this time. I agree with you.
Yep.
No. So another interesting thing about Hilbert is that he came with the concept of mathematical physics. You want to explain what is that?
Yeah. When you had brought that up in the notes for the show, I said, well, what is that? Is that I'd never heard that phrase before. I said, is that some special kind of physics that's different from the physics that we know? And it's not. It's just the fact that to do physics, you need to be able to describe it mathematically. And we think about the experiments of Newton as an example. It was all physical experimentation. For years and for centuries, the study of science was based on physical experimentation, and there was math tied to it. But the math and the experimentation went hand in hand.
Yes.
We are now at a time, and this, I would say, Hilbert probably opened the door
Mm-hmm.
for physicists to experiment mathematically. You look at all of the developments in physics in the past 100 to 150 years. So much of it would not be possible if it weren't for the idea of mathematical physics. One example, looking at the discovery of black holes and the description of black holes.
Yeah.
You can't create a black hole in a laboratory, and even if you could, you wouldn't want to.
Yeah.
But you can't do experimentation with a black hole.
Mm-hmm.
But you can describe it mathematically. You can make observations, and you can see, okay, well, let's describe this mathematically. Does the math match with what we see?
Mm-hmm.
And can we get even more detailed than what we can see by studying the math?
Another great example is Albert Einstein.
Mm-hmm.
When before it was proven, he has to put it in a mathematical way.
Mm-hmm.
His general theory of relativity,
Mm-hmm.
and he played with mathematical physics
Mm-hmm.
there, but his idea was so revolutionary that the physics at that time, they didn't want to adopt until there is a proof that came with the experiment of the deflection of the light of the star when it goes to the sun.
Mm-hmm.
That's when he came utterly famous. But he didn't did that experiment.
Yeah, he didn't make the observations of the experiment first. He did the math first.
Exactly.
Well, and that goes back to the quote that you just said before from Feynman, that we understand, we still completely understand the quantum world, but we understand it almost all of what we understand of the quantum world now. It's because we understand the math.
Yes.
We've just been a decade or a couple of decades where we've had microscopes, electron microscopes that have been able to see a very fuzzy image of atoms. We still can't see within an atom. So the experiments, the observations are very rough at the moment. But what we do know is all because of the math. The strengths of the fields within the atom, within a proton.
Yeah, and that's
strength
because
of an electron.
And that's because when you build the instrument, you have to have the math to in order to. If you don't have math, you cannot approach to do that. No,
you wouldn't even know where to start.
Exactly.
Yeah.
So we were talking a little about math and computers here, no? And I want to mention the next two persons. One is utterly famous, and the other one is unknown, no? So Alan Turing. Everybody knows, I think, by this time, Alan Turing. Everybody has seen the Imitation Game. Alan Turing, it's a British mathematician that was born in 1912, no? So everybody that sees the Imitation Game will see how the influence of his work, no, on encryption and decryption and building the machine. Some might say that was the first computer. I will say that it was a machine because a computer is a general purpose thing. No? But let's say that the basis of his math bring to the life to the first computer. No, so and that's a paper that he wrote. He wanted to do that, and that theory, that paper that he wrote, is the basis of the computers. No, but then he's famous because he helped break the code, and that's what we are going to talk about. The second one, it's Bill William Thomas. No, he's also a British mathematician. He's kind of the same age of Alan Turing. No, so they both were very intelligent people. They both were in Bletchley Park, which was the place that all these mathematical and deciphering place on all the message among the Nazis were decrypted. No?
Okay. So the British intelligence collected all of these mathematicians to work on decrypting these encrypted messages that were sent back and forth by the Nazis.
Yes, exactly. So let's compare right now the work of these two guys. No? So one of them invented the bomba machine. And for the guys that have seen the Imitation Game, they know already what's the bomba. The bomba machine was a machine that the Germans used to encrypt messages, and transmit to the other side in Morse code. When the war came, the Polish has done some work on decrypting the bomba machine, but the Germany invade Poland, so all that knowledge was transferred to Great Britain to start working on more of that. So the British inherit, they have the machines, they know the Polish method to decrypt the messages, but the German came with a stronger encryption methods on that, and then the challenge was, okay, we have the machine here. There's a lot of combination. How do I get fast enough to know the message? And that's the genius of Alan Turing.
Okay.
So he was fighting the bomba machine, and in order to do that, he created the Enigma machine. The Enigma machine plays with all the possibilities and also have some input about what possible message can contain in order to decipher the message. So, and he was a very, very pivotal, instrumental person to decipher that. What about Tutte? Have you heard about him before?
No, I've never heard of him before.
So Tutte helped Tommy Flowers design the Colossus machine. So the Colossus machine wasn't mentioned, I think, in the Imitation Game, in the movie, but the Enigma machine, everybody in the military has an Enigma machine because that's how they communicate in secret. Hitler want a machine that, first of all, will be more secure. Second, that doesn't need two persons, because in the Enigma machine, one is typing and the other one is looking at the bulbs to write the encrypted machine. So you need two persons to write the message. And Hitler didn't want that. He wants a machine that he owns only and then can encrypt the message to his most closest generals. So the Lorentz machine, this is how it calls the Lorentz machine. The Lorentz machine was, there wasn't many Lorentz machines. It was Hitler and his most closest general that received that machine. It was kind of over a typewriter, you put this Lorentz machine, and from typing directly start coding and transmit it. And this didn't transmit in Morse code. It transmit in ITA2, which is International Typewriting Alphabet or something like that.
Okay.
Oh, I'm sorry. International Telegraph Alphabet 2.
Okay.
So that was a different way of coding.
Okay.
So when the war started, the Allies know about the Enigma machine, and they cannot, sometimes they identify some characters that were not aligned with Morse code. What is this? What's happening? And because not unlike the Enigma, the Lorentz machine, they have just a few. Hitler has one, his most closest general. So there wasn't anything that they
couldn't get a physical machine.
Exactly. And there was this problem here on how are we going to decipher this message? This seems to be important. So what happened here is that in a transmission from Athens to Vienna, they were scanning the spectrum, trying to find something they couldn't find, and then in transmission from Athens to Vienna, the answer from the man from Vienna was, "Can you retransmit the message, please?" But he didn't answer with the code. He answered plain.
Okay.
So, hey, everybody, can you retransmit the message? So they have, previously
So
typed,
the first message.
yes,
Okay.
and then the second message was transmitted, but they noticed that the second message was a little shorter.
Oh.
So what they imply is the first message is the message, and
Mhm.
this is the same thing but a summary.
Mm.
And the message was only 4,000 characters long.
Mm.
That's all it takes to build Total, to
Wow.
figure it
Wow.
out.
Wow.
The machine, how many rotors, how it works,
Wow.
and to start deciphering the message.
Wow.
The funny thing that we don't know is that because we were able to intercept the Lorentz machine, we know it happened D-Day because they intercept a message say that was from Hitler to one of his generals saying, "Hey, no, the because Hitler know that they were preparing to invade Europe, continental Europe, in order to the Allies. No, the thing that Hitler didn't know was, is it going to be in Calais or is it going to be in Normandy? So the British intelligence tried to set up a plan to make Hitler think that the D-Day was going to be in Calais.
Yeah.
So to concentrate his focus there, so let Normandy with less defense so they can
Yeah.
penetrate.
Yeah.
And they intercept a message saying Hitler, no, the D-Day is going to be in Calais. And that's how they know that Hitler
that
has
it
taken
was
the bait.
Take the bait. Yeah.
And then they invaded from Germany.
If he had not been able to decrypt those messages, we wouldn't have known.
Yes. Yes.
Wow.
So that's how important this is. No.
Wow.
The other thing that will probably blow your mind is that I mentioned that Tommy Flowers helped create the Colossus because Winston Churchill didn't want this technology to go to Russia. He prohibited everybody to talk about the Colossus. He ordered to destroy all the Colossus. One was preserved in secret. And when Bill Tuttle was flying to United States, and they developed ENIAC, and they showed to the world ENIAC, he said, "Wow, this is 2 years later. That's kind of the same machine that I was building," but he couldn't talk about it because it was on the uttermost secrecy. Wow. And it is not until the 21st century that until 1970 that they declassify that.
Okay.
Wow. So that's what the level of genius of Bill Tuttle is.
Wow.
I want to mention these two parallels because, of course, I acknowledge William Turing. It's very intelligent, but when you approach history, there's you have to see what is in the intention of the person that that shows. No.
Yeah.
And
you can only talk about so much when you're talking about history.
Yes.
So you have to choose what you're gonna focus on, right?
My question is, why didn't they even mention about Total? You see the level of genius of this guy.
Yeah.
I mean, he didn't have the machine. He didn't see the machine until the end of the war. Yeah. But in his mind, he came up how this machine could work.
Well, and it shows what a blessing it is in the time that we live. We have so much information at our fingertips. We can look this up, and we have to be discerning with what we look, because we know that there's a lot of stuff out there that's not true. But but there is a lot of information out there, and we can learn about these figures that we didn't know about before.
Yes, exactly. So when we think about Roger Penrose, I also tied to my memories in my childhood, reading the Brief History of Time and the Universe in a Nutshell, no? And this was written by a famous physicist, Stephen Hopkins, no? But when I start to dive into what he wrote in both books, I see he mentioning a lot of times this name, Roger Penrose and I,
Mm-hmm.
Roger Penrose and I, Roger Penrose and I. No? So my mind has, who is Roger Penrose?
Mm-hmm.
No? And they were friends actually. They were both friends, and I tried to search a little more on Roger Penrose. No, Roger Penrose was born in Great Britain in 1931. No, he starts to, well, he has a lot of things that has developed, but one of the things that he's very famous is in having the mathematical foundations, so Stephen Hopkins can develop his black hole theories.
Mm-hmm.
No, I think that there's a famous thing about the diagrams that you want to talk about.
Yeah. I remember learning about the Penrose diagram, and it's a diagram that is used in describing what the physics is like around a black hole.
Mm-hmm.
And the thing that's very interesting is it was developed partly by Penrose to explain the motions and the relationship between space and time, and how it relates to something that travels at the speed of light near something that has a gravitational field as strong as a black hole.
Yeah, it's exactly how does other things behave when they come near a singularity.
Yeah.
You know? And the thing is that, and he uses light because light is the ultimate barrier
the fastest.
that we can have in whatever speed we in talking about speed, but the fact that he can come up with that concept, no? Because how we have the concept of the cone of lights, and the history prior and the future that we can see. How does this singularity, which is we are calling black hole, affects that? Affects time, affects space, affects the traveling per se.
There's a great YouTube channel that I love watching, and a lot of the times I make it through the whole video, but it's a lot of it is way over my head. But it's put out by PBS. It's called Space Time, and every episode talks about some theory, a lot of them groundbreaking theories in physics, and there have been a number of episodes where they've talked about different theories tied to black holes, and every single time they've illustrated the theory with one or even multiple Penrose diagrams all connected to each other. And it's fascinating. It's still way over my head, and I still would love to learn more about it. But it is an interesting way to view infinite space or infinite gravity, or things that are way beyond our concepts of anything that we see in our everyday life.
Roger Penrose was also concerned about people trying to understand the math. So he wrote a book actually. Similar to Stephen Hopkins, he wrote several books. Penrose also wrote several books. One of them is The Road to Reality. And it's the title is Road to Reality: A Complete Guide to the Laws of the Universe. That was copyrighted on 2004. So I bought that book. I say, that book has 30 chapters, and I was I want to understand the universe. Chapter 7 is as far as I go, because in chapter 8 I start flying. This is not.
Your brain started to melt.
Yes, exactly. So I need a mathematician to digest me more, a little more all these concepts. But it's fascinating how. But don't take me wrong. Roger Penrose did a great thing writing this book, because, as far as I know, the concepts were explained very detailed. When he tried to explain the math behind the concept, which is going deeper in chapter 8, that's when I start flying out. But that's if you are a mathematician, that's a book that you would like to read. No, that you like to read. No, and if you read it, please explain it to me. And
yeah. Let us know in the comments
Yes.
what it means past chapter 8.
But another thing that I want to highlight about Roger Penrose is how humble he is. No, he is an agnostic, so he say that his position about God is, he's not saying there's no God. He's saying that our mind cannot afford to understand, to grasp God. I want to read a quote from A Brief Story of Time that says this. No, I think I will say that the universe has a purpose. It's not somehow just there by chance. Some people, I think, take the view of that the universe is just there and it runs along. It's a bit like just a sort of compute and happen to be somehow by accident to find ourselves in this thing. But I don't think that's a very fruitful or helpful way of looking at the universe. I think that there is something much deeper about it. And in an interview in 2022, he says, consciousness must be beyond computable physics. So here we have a guy, he collaborated with Stephen Hopkins on developing all this great theory about black holes and how the universe is expanding. Even though he's agnostic, he's humble enough to say there is something greater than we cannot understand. No, and unconsciousness, which is which is our mind actually, it's something that cannot be computed. No, so that's really counter the current idea that there's no God.
Right. Well, and even that the brain is just a computer.
Yes, exactly. So I want to highlight that also from Sir Roger Penrose. It's Sir Roger Penrose. He was knighted. Wow. Because of that great achievement.
Well, yeah, it's something to be knighted for.
Yeah.
And it's also it's neat to know that there have been a number of mathematicians and scientists that have been knighted for their achievements.
Yeah.
They got very strong, very knight-like brains. You don't need to be good with just a spear and a sword to be a knight, right?
Yes, and that's a good thing, I think.
Yep.
Our last person here is Dr. John Lennox. No, please don't confuse by John Lennon, the singer. No, he's John Lennox with an X at the end. No, he is a very brilliant mathematician from Oxford. No, I will have to say that. I will just read his accomplishment here. No, he has a doctorate from University of Cambridge. He earned a second and third doctorate from University of Oxford. No, specialist in group theory. Again, this is coming. Remember Cantor? No, he has a special field in group theory here. He's emeritus professor in Mathematical University at Oxford, and emeritus fellow in Mathematics and Philosophy of Science and Green Templeton College. No. So he is a very smart guy, no? But I didn't know John Lennox as a mathematician, no? I started to know John Lennox as a Christian apologist, no? And how did I know about John Lennox is because there's a famous quote from Stephen Hopkins, kind of at the end of his life, that says, because there is a law of gravity, the universe can and will create by himself. No? So that phrase coming from a genius, from Stephen Hopkins, struck me. How this is saying that because there's a law of gravity, the universe doesn't need gods to be created. No, it just needs the law of gravity. No, and that position really struck me because until at that time I have Stephen Hopkins in so high consideration. No? And I was searching for what is the context of what he says this, and trying to
Mhm.
understand a little more. And that's when in my research I came from to come with John Lennox. No?
Mhm.
He was criticizing Stephen Hopkins not because of his works in physics, but
Mhm.
because of that phrase.
Yeah.
I remember one of his quotes saying, 2 plus 2 is 4, but that doesn't put $4 in my pocket, doesn't it? No. So the idea of having the description of something
Mhm.
doesn't make anything. No?
Right.
The idea that we have the description of something just means that there is a mind
Yeah.
that makes this, and this is how we
Yeah.
can prove that there's a mind.
Yeah.
No?
Yeah.
And he just brought this analogy.
Mhm.
If you see, a beach there, and you see a lot of shells there, but as you walk, you see some shells that forms the 4 letters HELP,
Mhm.
help.
Yeah.
Would you think that was randomly made, or because there is a structure there,
Yeah.
you immediately thought that there's a mind
Yeah.
behind that?
Yeah.
No.
Yeah. This view of intelligence, this that we can see intelligence
Mm-hmm.
kind of baked into the universe.
Mm-hmm.
And as we were saying before, with Cantor and his view on infinities, or
Mhm.
his discovery of an infinite number of infinities, that that people were criticizing him,
Mm-hmm.
probably because their view of God was so small. And as you're saying, even to today, to say that we don't need God because we understand gravity now. Well, okay, where does gravity come from? So we look at Pascal and his wager, to say, in all the ways that Pascal thought about who God was, and how it was logical to assume that a God exists. And you look at philosophers like Aquinas to say, that there's always something behind an argument that you make. You can always go back, but you can't go back infinitely, right? You have to eventually get to God,
Yeah.
that is the beginning
Yeah.
of everything.
Yes.
And so whenever you make a scientific argument, you always have to say, okay, well, this is the cause of this.
Yeah.
This, well, then what caused that? Okay, well, then this was the cause of that.
Mm-hmm.
We look at, we see that in the a lot of the theories coming out now, string theory, multiverse theory.
Mm-hmm.
There all these theories to say, well, what was the beginning of everything? Well, okay, that there might be a multiverse. We don't know, but what created the multiverse? You always have to go back and back and back.
Yeah.
And so I think it's just fascinating that that it doesn't matter how far you go back.
Yeah.
You always have to start with something, and that something has to be God.
Yeah. Or in the case of Stephen Hawking, a formula.
A formula. Well, who wrote the formula?
Who wrote the formula then? No, that's a very good point, because as John Lennox was saying, the fact that there's a formula doesn't give you the creative power of everything. A formula is a description, and that's really important that everybody knows. No, a formula is not the final explanation of something. A formula is a description of a phenomena that can be repeated. No,
Yeah,
that's very important to understand.
yeah.
No, and I want to have about John Lennox with a quote that he has in his site. No, he has a site that it says www.johnlennox.org. No, and there's a quote that says, "Either human intelligence ultimately owes its origin to a mindless matter, or there is a creator.
Mm.
It is strange that some people claim that it is their intelligence that leads to prefer the first one than to the second."
That's fascinating. That it's the people that say they're intelligent
Mhm.
to say, well, then I found the explanation for everything. You know, what is one of the greatest virtues in Christianity is
Humility.
humility.
Yep.
This ability to say, I don't know
Mhm.
everything. And you look at some of the greatest physicists in the past few hundred years, the majority of them have believed in God in one way or another. You look at the Psalms, the heavens declare the glory of God.
Yeah.
And I would say now that we understand the size of the universe, that is so much more true now than it was back then.
Yeah.
The more we see the structure of the heavens, the more we see the structure of the subatomic, the more it all declares the glory of God.
Yeah, because we can see how great and how infinite is his creation power, right? How fascinating is what he did. No?
Yeah. And when we see how it all works together.
Yes.
And even
in
to
harmony.
say that not only did he create everything, that the fact that he sustains everything, and in all of its infinite complexity.
Yeah, we have to do some when we start doing the physics one.
Yeah, I'm really looking forward to the series we're going to do on physics, because there are a lot of even now, I would say, especially now, so many interesting theories that are out there that I'm really looking forward to getting into.
Yeah. So I think we have concluded our math series here.
Yeah, and we have come a long way. And I think just to summarize all of it, I think it's so. One of the things I've really appreciated about this whole series is that we have seen from the beginning, from the Sumerians all the way up to today, this development of math, and as we said before, at the same time, a discovery of math as a framework that makes everything else make sense.
Yeah.
And we have slowly discovered over hundreds of years the complexity of this structure that sits underneath, almost like the scaffolding of the universe, that makes everything make sense.
So, is math real?
Is math real? Well, I think you can probably tell where we're coming from and what we think, but it seems to be.
Yeah.
And I hope at some point to have some experts on to talk more about that concept, and we will continue to delve more into that. But I want to thank you for joining us in this journey through the last 2,500 years, looking at the history of math, the development of math, and who knows where we'll go from here. Our next episode, we're going to take a short break from our discussion of math. We're going to do a little bit of a step back. Cesar and I want to talk about That Nerdy Catholic and why we're doing this, kind of a little bit of each of our backgrounds. This will be a good introduction to Cesar and who he is and why he has joined the Nerdy Catholic team. We're going to talk a little bit about the purpose of this channel and why we want to make these videos. So be sure to join us next time.
Please everything that you think about is math real, and any comment about the math history, let us know in the comments.
Yeah. Leave a comment below. As we said before, if we've missed anything, and even if we've made some mistakes in what we've said, please let us know. We are always open to learning more on this subject and any subject. If you want to keep up to date with what we're putting out and new things that we're doing, ways to support us, head over to thatnerdycatholic.com and sign up for our email list. We promise we won't spam you. We won't give your information out to anyone else. We just want to send you a couple of emails a month with the latest information of things that are going on in the nerdy Catholic world. If you think that we've earned it, we would love for you to like this video and share it with your friends. Subscribe to the channel and hit that little bell notification if you're watching this on YouTube. If you're listening to us as a podcast, we'd really appreciate it if you would rate our show on your podcast platform of choice. And you can always go over to thatnerdycatholic.com/merch to get very cool merch like these mugs and shirts and stuff. Show the world that you are a nerd and that you appreciate the intersection of the sciences and faith. So we will see you again next episode. Cesar.
A pleasure as always.
All right.
Bye-bye.
Bye.
System shut down.